Welcome student in the lecture 7. Here you can see I have shown you two different geometry. One is octahedral and the other one is tetrahedral. It means along with octahedral geometry, today we're going to start the discussion of tetrahedral geometry as well. In octahedral geometry or in our previous lectures, we already discussed the sigma interaction, sigma donation interaction and pi donation interaction. Now today we are going to discuss sigma donation, pi donation, along with that pi acceptance in octahedral geometry, and at the same time after that we're going to discuss the sigma donation interaction in tetrahedral geometry. You know that this is a tetrahedral and it is kept vacuum. This is a central metal ion, ligand 1, 2, 3 and 4, and it is oriented in a Cartesian way. This is the proper or arrangement for the tetrahedral geometry, as you know. So we're going to discuss only sigma donation interaction for tetrahedral geometry, and you know that in tetrahedral geometry sp3 hybridization is there. So these are the two things we're going to discuss in our today's lecture. This is the topic of the lecture number 7. Metal pi star LGO interaction in octahedral complexes. So pi star interaction that we need to discuss along with sigma donation, pi donation. So certain other discussion which we have done for sigma donation and pi donation is omitted. Only the focus is made for the pi star LGO interaction with central metal ion in octahedral geometry. And after completion of that, we're going to discuss the sigma bonding in tetrahedral complexes. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. First point which we need to discuss, that is the molecular orbitals of octahedral complexes with the ligand having pi star orbitals. Now these are the ligands which are having empty pi star anti-bonding orbitals which interact, which participate into the interaction, and it will receive electron through back donation from the metal ion. So the tradition of donation here get reversed, and instead of donation here acceptance will be taken place. Metal ligand pi bonding can involve either a partner as the pi donor. As already I've said, metal ligand pi bonding can involve either as a partner as the pi donor. So along with pi donor, we're going to discuss here pi acceptance as well. Consider a complex where ligand L is a Lewis pi acid containing pi symmetric acceptor orbitals in addition to full bonding pi orbitals. So that means there is pi orbital already there. We're going to discuss sigma donation, pi donation, which already we have done. Along with this pi orbital, it contains certain pi symmetric acceptor orbitals. These pi anti-bonding acceptor orbitals gain electron from the metal through back donation, and gaining electron means Lewis acidic nature. That's why here initially the from sigma donation and pi donation, ligand act as pi base, but when empty pi star anti-bonding orbital which going to accept the electron, that time the ligand's pi orbital act as pi acidic orbital, and there the metal act as pi base. Generally in further interaction which we have discussed, sigma donation and sigma donation pi donation interaction in octahedral geometry, metal always act as a acid there. Now here metal act as a base and it will donate back electron in the vacant pi star anti-bonding orbital of the central metal ion. So that is how this interaction is little bit different compared to the earlier one. These acceptor orbitals are generally anti-bonding type of orbital within the ligand. It means only those ligand which can participate in this kind of interaction which have this empty anti-bonding pi star orbital. If they do not have this anti-bonding pi star orbital, such ligand cannot participate in this interaction. Now, student, you need to think over here the limitation of CFT. Up to this, I haven't talked about the limitation of CFT, but here I will wake you up for the limitation of crystal field theory. In crystal field theory, there should be a electrovalent attraction, electrostatic attraction between ligand and central metal ion. And when this ligand approach to central metal ion, the d orbital which are degenerate will lose its degeneracy and split into T2G and EG, and we're going to get tetrahedral octahedral geometry as per the energy level arrangement of T2G and EG orbitals. So the ligand and metal need to come to Coulombic distance where this electrostatic attraction will going to result into bond formation. That is the main core thinking of crystal field theory. They will not include the contribution of s orbital, p orbital into this. They will not introduce any contribution of pi bonding in the complex formation. So there is a limitation of CFT which is clarified by this improved LFT, ligand field theory, or we can say molecular orbital theory. So after certain explanation, we're going to discuss in depth the limitation of crystal field theory as well. Now, as already I have said that such ligand which contain anti pi star and vacant orbitals in it, they can participate into this sigma donation, pi donation, and pi acceptance interaction in octahedral geometry. So many examples are there: carbon monoxide, cyanide, alkyl phosphine, and such ligand which contain vacant antibonding pi star orbital which can gain electron from the metal through back donation can act as this kind of ligand. Here also we can say the limitation is explored for CFT, that CFT will not say which ligand will split the orbital more effectively and which will not, or why certain ligand will split the orbital more effectively and why certain ligand should not split the orbital more effectively. That cannot be explained in CFT, can be clarified into this molecular orbital theory. Those example I have talked about, that is carbon monoxide, cyanide, nitrous oxide, triphenyl phosphine, alkyl phosphine, those ligands which have ability to form sigma as well as pi bond can participate. And here these are the two best example to explain the metal pi star orbital interaction in this category. The pi star orbital is more localized on carbon. Well, for this you need to see the molecular orbital diagram for carbon monoxide. Probably you have learned into your lower semester, where you probably have studied that the pi star antibonding orbitals are more localized on carbon atom comparatively to between carbon and oxygen. It will little shifted towards carbon and has a suitable symmetry for overlapping with T2G filled pi orbitals of the metal. It means that the metal will have pi T2G filled orbital from which it will donate electron and act as Lewis base. And this pi star orbital which is localized more on carbon atom in carbon monoxide will gain that electron as a back donation and act as Lewis pi acidic ligand, acidic orbital. So that you need to keep in mind. Certain time it will ask into MCQ, and you can address this question there as well. Well, in further discussion, the full bonding type orbitals are localized more on oxygen and are not available for pi overlap with T2G orbital of the center metal ion. If we compare the carbon and oxygen of carbon monoxide, carbon is going to interact with the metal, not the oxygen in carbon monoxide. Sometime it will be asked into MCQ as well, so that you need to keep in mind, because the symmetry will be on the carbon side, which match with the filled T2G orbital of the metal, but oxygen should not have that kind of anti-bonding pi star orbital which will going to match with the T2G orbital of metal, and so it will not participate into overlapping. The pi star acidic orbitals on the ligands are higher in energy than the metal T2G orbital. Pi star acidic orbital of ligand that is shifted on the carbon, if we're going to discuss the carbon monoxide as an example, then the energy of that pi star acidic is little bit higher in comparison with the T2G orbital of the metal. It means that from lower T2G of metal, electron will go into higher pi star acidic orbital of the ligand. So this is different type of interaction you will witness in this uh, example of hexa carbon monoxide metal complexes. See the MOED presented in the figure, we're going to see in the lower figure as well, for the octahedral Ml6 complex, where ligand is having sigma plus pi star type of orbitals in this example of the octahedral complexes. When the pi star LGO ligand group orbitals overlap with the T2G orbital, that is the filled T2G orbital of metal, to give pi MO, the T2G pi star will become a bonding type, get depressed, and thus increase the delta O. It means the splitting energy is going to be highest in comparison with the earlier two interaction, where only sigma donation and pi donation is concerned. We learned that in sigma donation the splitting energy is fair enough, while in T2G while in a pi donation interaction, T2G is shifted towards anti-bonding, so the splitting energy get decreased, and in the sigma donation and pi donation interaction. While in sigma donation, pi donation, pi acceptance, you can see here the splitting energy is going to be more and more higher. So if we'll compare the splitting energy in these three interaction, only sigma donation has splitting energy. Sigma donation and pi donation has lower splitting energy, and sigma donation, pi donation, and pi acceptance has highest splitting energy. That means that only sigma donation comes in between. Lowest is sigma donation and pi donation. Little higher splitting energy is of only sigma donation interaction, and highest splitting energy is of sigma donation, the pi donation, and pi acceptance interaction. So that you need to keep into mind when it is asked in certain exam. The energy ordering of various levels has been taken as the construction of MOED we're going to discuss into figure. That is, sigma LGOs are having lower splitting. Then after pi LGO, pi LGO से ज़्यादा energy will be of 3D. 3D से ज़्यादा energy that is of NS. NS से ज़्यादा energy pi star LGO, and highest energy is of NP. So here this is the ordering in the MOED for this pi acceptance interaction. Please keep it into mind. In a certain exam, this kind of ordering will be asked for a single line question, either in the MCQ, that what should be the energy ordering into MOED of only sigma donation, or either sigma donation and pi donation, and sigma donation, pi donation, and pi acceptance interaction. So this is the energy ordering of sigma donation, pi donation, and pi acceptance interaction between metal and pi star LGO. So that you need to keep into mind as well. There are many pi star LGOs as there are pi LGOs. So जितनी pi LGO would be there with the ligand group orbital, the same number of pi star orbital would be there as well. So here also I would like to advise you to go for the MO diagram of carbon monoxide or cyanide once again, and you can notice there uh, that the number of pi BMO is equal to the number of pi A star ABMO. So that can be considered over here as well. So again, in a previous case which we have studied, sigma donation and pi donation interaction, there we studied that pi donation have 12 pi LGO. Here also pi star would be 12 pi star LGO antibonding orbital the ligand should have. So that you need to keep into mind. Now here you can see that MOED diagram for the pi acceptance interaction. This is the molecular orbital, atomic orbitals of central metal ion, 3D, 4s, 4p. 3D is lower energetic, 4s is little higher, 4p is even higher. This is MO we're going to discuss later. And this is LGO. LGO contain sigma LGO where A1G, T1U and EG symmetry symbol is there. Pi donation LGOs where T1G, T1U, T2G, T2U would be there, and pi star antibonding LGO there also T1G, T1U, T2G and T2U symmetry would be there. Now you know that metal ion have EgT2G, A1G and T1U symmetry symbols, and when this interaction will taken place, this number of molecular orbital is going to be generated. Here this is sigma BMOs. Sigma BMOs has lowest energy, highest stability, and it will remain closer to the LGO, sigma LGO. So they will going to demonstrate the property of LGO. Already we have discussed so many times. A1G, T1U and EG. This symmetry symbols is there in the sigma BMO. Higher than that, we have T2G pi BMO. T2G pi BMO, that is the interaction of T2G of central metal ion and T2G symmetry of the pi donation LGOs, and that result into this T2G pi BMO, bonding molecular orbital. Now T1U symmetry, since we have T1U symmetry over here which already participate into sigma interaction, therefore it will not going to participate fully into pi interaction, but it has partial interaction with pi. So this T1U is having partial pi character and partial non-bonding molecular orbital, so it remain very closer to the energy level of the pi donation LGO, while T2G and T2U, they act as completely non-bonding, but they have little pi symmetry as well. They have little pi symmetry as well. And then after we have another energy level, that is the pi donation. And you can see that pi donation energy level is little lower than the 3D, that is transition metal elements energy. It is little lower than that, and 3D is going to have little higher energy. So that energy leveling you need to maintain when you are going to draw MOED diagram for any complex compound. Please keep it into mind, this energy ordering. First we are going to have A1G, then T1U, then EG. Then we will going to have sigma LGO, then we will going to have pi T2G BMO. After that we have T1G pi and non-bonding, that symbol you need to put it over here. Then after we'll have pi donation LGO, and at the same level we have T1G and T2U non-bonding. And then after here we have the 3D, that is N-1D, will include EG and T2G. That T2G is little shifted to anti-bonding side, and therefore it will shifted upwards over here. So it has little higher energy comparing with the atomic orbital of 3D T2G pi star. And then after we will have EG pi star, and there should be a contribution into this T2G pi star, that is pi star anti-bonding orbital of the LGO as well. And here we have 4s, that is A1G symmetry. A1G symmetry have one contribution to sigma BMO and other contribution to sigma anti-bonding molecular orbital. While T1U, as already I have told you, that because it participate major into sigma interaction, it has sigma interaction at the same time it has little pi interaction as well, partial pi interaction as well, and it has partial pi interaction with the T1u pi star anti-bonding orbital of LGO as well, while T1g and T2u pi star anti-bonding orbital act as NBO non-bonding molecular orbital, and its energy level is quite similar with this one. Now keep it in mind that pi star anti-bonding LGO is having little higher energy compared to 4s, that is A1G symmetry, and little lower energy compared to this NP-T1U symmetry. And then after we have highest T1U sigma and pi anti-bonding character it has, and this T2G is going to show, because it is a filled orbital of central metal ion, so it will going to demonstrate a metallic character, and this will demonstrate a ligand character, this will demonstrate a ligand character. So that is how this kind of interaction will going to found into sigma donation, pi donation, and pi acceptance interaction in this complex formation. So with this, octahedral geometry comes to an end, and we're going to discuss a new geometry. And in this new geometry, we're going to start the uh, tetrahedral geometry first. And in before we start this tetrahedral geometry, let us have little discussion on this pi star antibonding orbital. It may be unlikely that the ligand such as carbon monoxide, cyanide use simultaneously the donor and acceptor orbitals for the interaction with appropriate metal orbitals. As already explained earlier, in the case of carbon monoxide, the filled pi bonding orbitals are more localized on oxygen rather than on carbon, and would thus have negligible interaction with the metal orbitals. In such case, the MOED of the type presented into the earlier figure has to modify to incorporate this no interaction situation for T2G part of the pi LGO. A diagram partial given we're going to see in the next slide maybe then be more appropriate than the T2G pi star LGO interaction with the metal T2G becomes maximum. So here there is a correction in the above diagram where this T2G interaction, this is the atomic orbital of central metal ion, it's a partial MO is shown over here. T2G instead of already we have shown into the above diagram that it is shifted upper side, higher energy side, instead it will going to shifted lower energy side, and will going to get a large splitting energy. So comparison with the sigma donation and pi donation, the sigma donation, pi donation, and pi acceptance interaction have maximum splitting energy, and that can be explained. These three different category of splitting capacity of the ligand can be explained through MOT. It cannot be explained through crystal field theory. That is a limitation as well, and that can be categorized into two parts. One is highly occupied molecular orbital, that is HOMO, and this one, because less electron will enter into this due to the large value of the splitting energy, less electron enter into EG star, so it is LUMO, lower occupied molecular orbital. So this is lower occupied molecular orbital, and this is T2G star. So this is the correction that you need to keep it into the molecular energy diagram which is shown earlier, because that is shown earlier that this T2G is shifted up. Instead the T2G will be little lower than that of the T2G energy level of the central metal ion. So I will going to show you again that in this energy diagram will show that T2G is little bit up. Instead at this energy level T2G is little bit down, and the splitting energy get increased, and that is why electron which is there in the T2G will not enter into EG, and therefore T2G is completely filled. It is called a high filled molecular orbital, HOMO, highly occupied, higher occupied molecular orbital, HOMO, and this is because less electron will enter due to high splitting energy, less electron enter into EG, it is considered as LUMO. So that concept we have discussed over here. On other non-bonding molecular orbital from pi star anti-bonding LGO are not shown in the diagram, and delta O, that is splitting energy, is shown as high occupied molecular orbital and lower occupied molecular orbital separation, which can be experimentally determined, and that can bring more limitation in crystal field theory that you need to keep into mind. Now let us discuss sigma bonding in tetrahedral complexes. And when we begin this sigma bonding in tetrahedral complexes, let me make you remember that we have started this theory sigma donation interaction in octahedral geometry with four steps. So those four steps you need to keep it into mind. First step is find out the valence orbital of central metal ion, and we need to assign symmetric symbol to each valence orbital of central metal ion, which will going to participate into overlapping. The second step is a step of LGO formation, and we're going to show orbital picture diagram for LGO formation as well. Third step is MO formation for wave function, MO formation, and last and for not least, fourth step is MOED formation. So all these four steps today we are going to discuss for sigma donation interaction in tetrahedral complexes. And tetrahedral complexes have sp3 hybridization, tetrahedral geometry it is there that you need to keep into mind. Then we're going to start this. Let us consider Ml4 tetrahedral complex where L is the only sigma donor ligand, and sigma donor, that means it is pi basic in nature. Please keep it into mind. It would be asked into MCQ that Ml4 tetrahedral complex contain which kind of ligand, pi acidic, pi basic, both and none. So you need to select pi basic nature because it is only donation. The high symmetry of octahedral Ml6 complex, which we all just discussed, that has made the method very simple because the metal valence orbital classified into sigma and pi type. That bifurcation we need to do over here. This may not be the future anymore with the lower symmetry such we're going to see into tetrahedral geometry. There the things will little change. The MO method can be worked out through the results may not be obtained simply. There should be a different uh, bifurcation compared to the octahedral geometry is there into tetrahedral. So let's start with the four-step explanation of MOED formation for tetrahedral geometry only sigma donation. The step one is classification of metal valence orbital into sigma symmetry. First step, consider Ml4 tetrahedron as being inscribed into a cube structure. We're going to see how it is there in the cube structure. Work out the character system of this sigma vector. That sigma vector as from this tetrahedral character table. A instead of A1G and T instead of T2G. So here G and number will not be there. So this A will indicate a singly non-degenerate orbital and T indicate triply degenerate orbital. And that triply degenerate orbital is only symbolized by T. From this character table we have obtained this symmetric symbol A instead of A1G and T instead of T2G or T1U. So neither T1U is there nor T2G is there. Instead, we have only T. That means this T will represent Px, Py, Pz, and this T also represent dxy, dyz, and this zx. So that you need to keep into mind. That is how this theory get little differ compared to the octahedral geometry. That you need to keep into mind. I am going to discuss both this simultaneously so that you have compare and contrast of these two theory as well. With the help of standard reduction formula and a tetrahedral character table, we can say that the tetrahedral group we found corresponding atomic orbital of central metal ion as A1 as 4s orbital and T1 as 4px, 4py, 4pz, and T1 as 3dxy, 3dyz, and 3dzx, because here there is no notation of u or z, that is zeroed or unzeroed in tetrahedral geometry. Therefore, T1 is assigned to both 4p and 3d orbital, and in 3d orbital specifically 3dxy, yz, and zx. So that is how the things little differ in tetrahedral geometry comparison with the octahedral geometry. This is the we can say Cartesian coordinate system. Already I have explained in the earlier starting that this is the central metal ion and it is inscribed into a cube: ligand 1, ligand 2, ligand 3, ligand 4, and this is how X, Y, and Z Cartesian arrangement would be there. So this picture is the molecular geometry of Ml4 tetrahedron and it is inscribed into cube showing the coordinate axis and sigma vector. This will indicate sigma vector, sigma 1, 2, 3, and 4. Sigma vectors representing in the metal sigma hybrid orbitals. So the orientation comparing to the octahedral geometry, it is completely differ, so that you need to keep it into mind. Well, since we do not know the extent of participation of this p and d orbital of T2 symmetry in sigma bonding, we have to use both the set to write down the corresponding wave functions for the LGO. It means here the T2 symmetry uh, is for p orbital and d orbital. The same symmetry symbol is there. So either p orbital will participate into sigma interaction or d will participate into sigma interaction. That is not known over here. But we know that in tetrahedral geometry, the approaching direction of the ligands for ligands to the central metal ion is not axial. They come through planar. It means that here the xy, yz and zx, which is a planar orbital, they will mainly contribute into sigma interaction comparison with the px, py and pz, which is an axial orbitals. Let's see how it would be. A pictorial approach may be used to arrive at this function, which are listed into this tabular form, where you can understand that which kind of interaction it would be. And this table, if you keep it into mind, it would be easy for you to draw the pictorial diagram as well. Here you can see that symmetry label A1 and T2 is there. A1 is it is for 4s orbital, and 1 by 2 sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. You know that s orbital is spherical in shape and it is spread in all the direction equally symmetrically, and therefore all the ligands coming from either axial side or coming from the planar side has to interact with 4s orbital, and therefore all interactions are positive interactions, sigma 1, 2, 3, and 4. Now T2 for px, we have 1 by 2 sigma ligand 1 is going to have a uh, positive terminal overlapping as far as BMO is concerned, and ligand 2 has negative interaction overlapping lobes. Ligand 3 have positive and ligand 4 have negative, and that is the way we have this all symmetry labels and LGO formation is there. And this, if you know, then you know how to represent pictorial diagram of the interaction between LGO and T2 orbital, atomic orbital of central metal ion. So please, you need to keep these things into mind before drawing the pictorial representation of the interaction between LGO and central metal ion in tetrahedral geometry. So please keep these symbols plus and minus into mind so that you can show the pictorial diagram more effectively. Here the figure 1 will represent the pattern of metal 4s and 4p orbital, that is A1 and T1 symmetry with the p sigma orbital of central metal ion as a p sigma orbital of ligand in tetrahedral complex, and we're going to show it into Cartesian as coordinate system only for figure A. Figure 1a we represent Cartesian system, and rest you need to understand yourself that this way the x, y, and z axis are oriented over here as well. So here the interaction of for ligands with 4s orbital, and already I've said that 4s orbital is spherical in shape and is spread into x, y, and z orbital uniformly. So all these ligand, because here you can see that there is a larger distance but this distance you can't compare this distance over here because the picture is little bigger. Actual arrangement is angstrom in size, angstrom into distance, and therefore you can see that there should be very fair overlapping take place between these positive lobes of ligand 1 with this s orbital, positive lobe of ligand 2 with s orbital, positive lobe of 3 with s orbital, and positive lobe of ligand 4 with s orbital, and that is why this sigma 1, 2, 3 and 4 are all positive interactions. While with this pz orbital, pz orientation, you can see that that is z axis, so this is a z orientation. There we can see that a plus 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 plus, that means ligand 1 and ligand 2 have positive interaction, so plus plus sign would be there. And here you can see that minus lobes will going to interact with the minus of the L4, minus lobe will going to interact with minus with the L3, and that is minus minus. But this plus and minus is not a positive negative sign, it is a upper lobes will going to interact, and this is lower lobes will going to interact with each other, and that result into plus sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. So that you can see over here in a PZ. And now Px and Py, the next pictorial presentation we're going to see that how Px and Py is going to orient, and it's going to overlay with this. In Px, you can see that ligand 1 is going to have a positive interaction with this Px, while ligand 2 is going to have negative interaction with this ligand. So this ligand 2 is going to have a negative interaction with that one. Ligand 3 is having positive interaction, and ligand 4 has negative interaction. So this plus minus kind of orientation overlapping is there between for px, that is T2 symmetry, with the T2 symmetry of central metal ion, that is px of the central metal. Similarly for py also this arrangement is shown, and this is the T symmetry px for py for pz. Now we need to discuss T symmetry 3D xy, 3D xz and 3D yz. This is a Cartesian arrangement that is shown for dxy orbital. This is dxy orientation, and with this dxy orientation ligand 1 has or interaction with minus, so it is minus minus shown over here. A ligand 2 has also minus minus interaction. Ligand 3 has because it is back side, this is front side, so minus minus interaction, and ligand 3 has plus plus interaction, and ligand 4 has plus plus interaction. This will represent BMO. It will show this as anti-ABMO. 1 and 2 is going to plus, 3 and 4 is going to minus, and that is how this representation plus and minus sign is for this edges of the cube shown to represent dxy orbital. Here also you need to assume that dxy instead dy xz, and in this dxz this kind of interaction is there, sigma 1, sigma 2 minus, sigma 3 minus and sigma 4 plus. So this is figure 2 will indicate the T2 symmetry for 3D xy and xz. Now this is T2 symmetry for yz. In the C, picture C will have T2 symmetry for yz. So here yz arrangement is there for central metal ion, and in yz ligand 1 has negative interaction, ligand 3 has negative interaction, 2 and 4 has positive interaction. So this is the pattern of the overlap of d metal orbital of T symmetry, and picture 1 which we will see earlier that has Cartesian coordinate system, and the same system can be applied for B as well. After learning this, we need to have a little discussion on this pictorial diagram, that in this figure 1 and 2 the metal ion is shown at the center of the cube, and the alternate uh, uh, corner of the cube the ligand is going to be arranged in a tetrahedron way. The Cartesian coordinate axis, that is xyz, are shown as passing through the middle point of the pair of the opposite faces of the cube. So that you need to assume a little bit. If you assume in a proper way, it will be visualized. I will going to show you how it going to orient when we have a classroom interaction. after the normalcy of pandemic situation. Each ligand is shown as using p orbital along the bond direction for overlap with a positive lobe of the p orbital oriented towards the metal ion at the center, and that is how the overlapping will result into positive overlapping. All the conventions adapted for positive or negative combination of the orbitals are quite clear stated into this figure 1 and 2, which already we have gone through in that figure. And since the s orbital of A1 symmetry is spherical in shape with positive sign, where gives a type of LGO wave function, we're going to see over here. This is the LGO formation of 1, 2, 3, 4, and that can be represented over here into this sigma 1 orbital as well. This is S symmetry, and we're going to see the LGO formation. This is the LGO formation for PZ. This is the LGO formation for PX T2 symmetry, PY T2 symmetry as well, and this is the LGO arrangement for T2 symmetry DXY, XZ, and DYZ. So that is how we can represent this arrangement. Each ligand is shown as p orbital along the bond direction for the overlap. Already we have discussed. When we consider the p orbital overlapping with the ligand p sigma orbital, there should not appear to be direct overlap. Yet it is possible to work out the interaction for obtaining the wave function of LGO T2 type. The figure 1 through B and D, we're going to see what B and D would be. Figure 1, B and D. So this is D and D arrangement, and here this is B arrangement, this is B arrangement, and this is your D arrangement. Figure 1, B and D arrangement we have talked about. Yes, figure 1, B and D that illustrate that the p orbital of the central metal ion can be best represented as its lobes touching the midpoint of the opposite face of the cube along any particular axis. When you see the diagram, you will found this arrangement, and it is shown into figure B that pz orbital of central metal ion is shown with the positive lobe projecting into the midpoint of the upper face of the cube. Upper face of the cube, that is a z direction, and negative lobes into lower face of the cube. So that way the orientation of pz orbital is there, that you can see into the figure as well. The positive lobe for pz orbital can have effective possible overlap with the nearest L1 and L2 p sigma orbital. Similarly, negative lobes will going to overlap with 3 and 4 sigma orbital, and hence we're going to found the wave function which representing this overlapping. From the table we can write as this: psi t2 pz is half sigma, that is plus sigma 1 plus and sigma 2 plus. This 2 is a positive lobes have interaction resulting to BMO, and this is negative lobes going to interact. So positive and negative will not, again I will repeatedly say, it not indicate positive or negative value. It is a upper side or lower side interaction which result into BMO represented over here. Similarly, by appropriate projection of px and py orbitals into the faces of the cubes, we can obtain the expression which we can see into figures C and D, which already we have seen there. So let me represent the wave function associated with px, that is half. Here the lobe of ligand 1 and 3 interact with the positive orientation of px, and ligand 2 and 4's negative pole will interact with negative side. Similarly for py, 1 and 4's negative lobes will interact with negative side of the Y orientation of central metal ion, and positive lobes of ligand 2 and 3 will interact with the positive lobe of the Py of the central metal ion. So that is how you can represent the LGO pictorial orbital energy level diagram. By the same analog, the metal d orbital, that is T2G set interaction, can be obtained as well. That is in a figure A. We're going to see how dxy, that is in a xy plane, that have four lobes directing toward the edges of the cubes. Let's see how it will at the edges of the cubes. So this will represent this edge, this to the front, this to the back side edge, and this to this side edge. And that is why it is a planar arrangement, because it is not in the axial side of any center of the face. It will between the two center of the faces. At this side the orientation would be there, and that is how this orientation will result into this kind of arrangement, where you can see that ligand 1 and 2, ligand 1 and 2's minus lobe will interact with this minus lobe orientation of the dxy plane, and ligand 3 and 4, ligand 3 and 4 has positive lobes interact with this positive lobe of the dxy central metal ion, and that result into PMO formation. Once again, following the rule of nearest lobe p sigma orbital interaction, we can obtain the wave function for its LGOs, and that LGOs as psi2 dxy half. Again, 1 and 2 have minus interaction, 3 and 4 has positive lobe interaction, result into PMO. Do not forget that the approaching ligand direction is from the axial side, not from the planar side, not from the axial side. Similarly, figure B and C for this YZ and ZX illustrate the interaction with the T2 symmetric d orbital set, and a partial of all these LGO wave functions reveals that the PZ, DXY, PX, and DYZ and PYDXZ have the same wave functions, with only the sign reversal would be there. Sign reversal, as I already said, it is not a mathematics, so sign reversal is not a factor, but they have similar kind of wave function arrangement. You can see over here T2G, T2PZ, that is plus plus minus minus interaction, and that when you are going to put a minus sign to T2 dxy, then both are going to be same one. That means this 2 is going to be minus in T2 dxy, and this 2 is going to be plus in T2 dxy symmetry. Therefore, the LGO obtained for the overlap with the metal p and d orbital with T2 set is quite similar, and the remaining orbital, that is dz square and dx square minus y square, that is E symmetry, not G. G just stands for zeroed, and this is not a symmetric arrangement, so we're not going to put that G subscript over here. Only E symmetry, and it is a doubly degenerate. Dx square and dx square minus y square are non-bonding when only sigma bonding is considered in the tetrahedral complexes. Their symmetry can be read easily from the TD character, tetrahedral character table, and that way we're going to represent. Now step 3, that is the formation of molecular orbital, sigma molecular orbital diagrams. So as discussed in the case of octahedral complexes, it is easy to write the wave function of the molecular orbital for tetrahedral complexes as well. We have a wave function associated with A1 symmetry, A1, right? A1, not 2. It is a typological mistake. A1 star, and that is represented as N1 A1S plus or minus half 1, 2, 3 for all positive interaction. This is for PZ, bonding and anti-bonding. Plus is for bonding, minus is for anti-bonding. This is for PX, bonding and anti-bonding. N3 represent the normalization constant. This is for PY, N4 is the normalization constant, plus is for bonding, minus is for anti-bonding, and there's the wave function associated with Py. This is T2 symmetry for dxy, and N5 is the normalization constant, plus is for BMO, minus is for ABMO, and that is much in the same way dyz and zx can be represented as the MO sigma orbital of tetrahedral geometry. After MO formation, we know that step number 4 is our MOED construction. In MOED construction, we are going to form a qualitative diagram, and it is represented into figure 3. In our next slide, we are going to see the ordering of various orbital is sigma LGO has lower energy than after 3D, that is n minus 1 3D atomic orbital of central metal ion, उससे ज़्यादा energy for s orbital atomic orbital of central metal ion, और उससे ज़्यादा energy for p of atomic orbital of central metal ion is there in the ordering. The most stable and lowest energy as usual is A1 symmetry, that is sigma A1 sigma symmetry. This is a particular mention here because this is the only instance where the overlap is direct and maximum overlapping is going to be obtained. A1 other molecular orbitals are result of a weak interaction. A1 is comparatively strong interaction since no case was there as a direct overlap under tetrahedral stereochemistry. Because of this weak overlapping interaction between the metal hybrid orbital and LGO, the energy separation, that is a gap between high occupied molecular orbital and low occupied molecular orbital, or we can say between T2G, that is T2 star, and E non-bonding orbital is not much large compared to uh, the octahedral symmetry. This is little low splitting energy, and here also CFT cannot say why in octahedral only sigma donation has large splitting energy and why in tetrahedral symmetry only sigma donation the splitting energy is little bit low. The T2 sigma bonding molecular orbital has mixed metal P and D of T2 set character. Hence, the same is the shown in the MOED diagram in this figure 3. You can notice that how the arrangement of only sigma donation MOED generation is there for the tetrahedral geometry. You can put any example over here. A1G has the lowest energy, that is A1G sigma BMO. उससे ज़्यादा energy molecular orbital, this is a part, this is the atomic orbital of central metal ion, and this is LGO part. So in molecular orbital, A1G sigma symmetry has lowest energy high stability, and T2G is little higher energy, that is sigma BMO as well. और उससे ज़्यादा उससे सटीक energy, उससे लगी हुई energy little higher, that is 4 LGOs from ligand group orbital, and they donate pair of electron into this sigma BMO, and therefore this sigma BMO represent a ligand character more, and that also cannot be explained into CFT why certain atomic orbital will represent ligand character and why certain orbital will represent metal character. That can be only explained through MO diagram over here. Now you can see that since E, that is dz square and dx square minus y square has no direct interaction with 4 ligand coming from the planar side, and therefore they are not participating into overlapping, hence its energy is quite similar with the energy of atomic orbital of 3D, and they can act as non-bonding molecular orbital, while T2, that is anti-bonding orbital, and the distance between these two is a splitting energy which is less compared to the only sigma interaction in a octahedral geometry. Then after the T2 of MO, little higher energetic, that is NS, that is 4s A1 symmetry. उससे ज़्यादा A1 anti-bonding molecular orbital, or in between this we have NP, that is T2 symmetry of atomic orbital of central metal ion, and highest energy of T2 sigma star. This is the MOED diagram for tetrahedral only sigma interaction. Well, student, you will miss this. St. Xavier's College, Ahmedabad. Uh, thank you for paying attention to this video lecture. I hope you have learned something with this comparison with the earlier video lectures. And I always inspire you to ask questions because it is a beautiful way to gain knowledge. So friends, please ask question in the chat box, or either you can email me